Calculus is AP Calculus 3-5 curve sketching. Today we're going to be sketching quite a few curves. But first, let me, Mr. Sindel, check whether you, my AP Calculus class, know how to graph the graph of x squared. F of x equals x squared. Do it. See if you remember. Where's the first point? It's at 0, 0. It should be at 0, 0. You need to graph the rest of them. Graph y equals x squared, or f of x equal to x squared. There's your first point. I helped you out. How do you graph this? Let me walk around and see if you can do it. All right, it looks like you guys are getting it. You know that when I square 1, I have a height of 1. When I square 2, I have a height of 4. 1, 2, 3, 4. And it is symmetric across that y-axis and then curvy. It has curves. Okay, well, when I have lag on the computer, it is not curvy. So roughly like that. That is the parabola. All right, this is the same graph, f, 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 but now taking the derivative, taking the double derivative, taking the derivative of the derivative of the derivative. I want to graph all of these graphs by hand. We did this with a computer and you just watched it. Now you have to actually do it. So, shout it out. Derivative of x squared is?
2x.
Yep. What is the graph of 2x? Go ahead and do that now. All right, hopefully you had something that looked like this with arrows on the end. 2x, it went through the origin, had a slope of 2. That means from the origin, I went right 1, up 2, right 1, up 2, just like stairs. Yes, yes, nod our heads, yes. All right, cool. Now, derivative of 2x is? 2, graph 2. What does that look like? Is that a vertical line? Is that a horizontal line? See if we remember how to graph that. It would be a horizontal. Yep. It has to be a function. A vertical line would not be a function. It does not pass the vertical line test. So there's the graph of y equals 2. And take the derivative of 2 and I get 0. Graph 0. All right, so interesting to see how to graph these by hand. We had this. What type of graph was this? Was this linear, quadratic, exponential? What type of graph was this? Quadratic. This is constant. Yep, and this is another constant. So let's actually label those. So this was a quadratic. You can just say quad, and if you don't know that that stands for quadratic, you can write out quadratic like that. Then we had linear, then constant, and another constant. And you would be correct in saying that these are linear because it still is a line, but it is constant is even a better definition, I would say. And some people might even call you incorrect if you said that they're linear. So let's do another example. We have 4 examples here, front and back, and then we're done with the notes. So the graph of G now looks like that. And this is sketching for a reason. It's not actual graphing. Just roughly guess the graph of G prime. So you know that this is this type of function. What does G prime look like? I want to walk around and see what we're graphing. Go ahead, just like we're doing before. This goes to this, this therefore goes to what? Do a rough sketch. All right. And it looks like the 2 people that I saw had it correct. It is a line down here. And I have a question for you guys. Why is it a line? Oh, I hate it when there's lag and then it doesn't write correctly. Why is it not a line up here?
Because the slope is negative on G.
Boom, yep, slope is negative. If the slope is negative, that means when I take the derivative, I will have a negative constant. So I actually want to say what these things are. This is a negative. The way I say negative is a negative with a circle around it, so it doesn't look like it's like a hyphen. So that's negative. Positive would be a plus with a circle around it. So this is a negative linear. Therefore, when I take the derivative of a negative linear, it turns into a what?
Negative constant.
Negative constant. And I feel like I actually want to color code that because I'm taking the derivative. So my derivatives I always do in red. So this is a negative constant. All right, and moving to example 2. First of all, what type of graph do we have? Positive or negative? And then what actual graph do we have? It is a positive what? Quadratic.
And negative quadratic will look like a sad face, right?
Sad face or rainbow, yep. Rainbow is a little bit happier than a sad face, I guess.
Yeah,
that's why we did it.
Negative quadratic is sad. Negative.
Okay, yeah. Maybe negative is is synonym for sad.
Or if you're feeling positive, it's a smile.
Okay, that's a good way to remember it then. Sad face, smiley face. So the derivative of a positive quadratic is a what? Positive linear. Go ahead and graph a positive linear. But be careful about this one. This one I am going to be very specific. You need to look for where you have a critical value on the graph of H. Where is a critical value? What is the definition of critical value? Shout it out. It's on the tip of your tongue, always. Critical value?
F equals 0 or does not exist.
Exactly. F prime is what on this graph? Is it height, slope, or concavity?
Slope.
Slope. So by Ben's definition, it's where the slope is 0 or where the slope does not exist. Where is the slope 0 or does not exist? Point to it on your graph and I will see. I can't actually see, but I assume that everyone's pointing to that spot right there. You can shake your heads yes. All right. So that is where it's equal to 0. That means when I take the graph of H prime, my critical value is going to be at that same x-coordinate. Here's my x-coordinate right here. That same x-coordinate over here, I should have a critical value of 0. What does a critical value of 0 look like on a graph of H prime? Does that mean it's going to be curvy like that? Does that mean it's going to be passing through it like that? Does that mean, like, I need to know graphically what a critical value looks like on the graph of a derivative. Graphically, what does it look like?
Where it passes through the x-axis?
There it is. It has to pass through the x-axis because the height has to be equal to 0. The height is now the derivative. All right, so it's either going to look like this or like this. I know which one it's going to be because I've already defined that it's going to be a positive linear. So I'm going to come back here to my line tool and go right through there. Sound effects make everything better. I don't know if you guys knew that. There's your positive linear. And let's go ahead and label that too. I should have done that in red. I keep forgetting. Okay, this is our critical value, our CV. Our CV. Our critical value. What is the definition of F minimum?
Negative goes to positive.
When what
F
is
prime, I meant.
yeah, F prime goes from negative to positive. Here's F prime, or H prime in this case, went from a negative to a positive. What is the definition of relative extrema?
F double prime does sign changes.
Yeah, close. Slight error.
Only F prime.
Only F prime. F prime sign change. What about F max?
When F prime is going from positive to negative.
Positive to negative. Perfect. Okay. Just make sure we have those on the tips of our tongues because we always need to have those in the backs of our minds. Perfect. So that's example 2. The CVs, the relative extremas, all of them have to match up from graph to graph. All right. Let's look at example 3. Graph of J. And I need to go to the back. Okay. Graph of J. What type of function? Positive and negative, and then the actual parent function. What is this thing?
Should be a positive cubic.
Positive cubic like that. You have a small error. Let's see if someone can find it.
Oh, negative.
Negative cubic. Why a negative cubic?
Oh, because it.
Oh, because of the slope from the one endpoint to another.
That's a good way of thinking about it. So like from this endpoint to this endpoint, the slope would be negative. That's a good way of thinking about a negative cubic. All right. For this one, I want to look at the relative extremas, specifically the subtypes of relative extremas, which are 2. They are, and exactly, minimum and maximum. So go ahead and put points on the minimum and maximum. It's pretty easy in terms of the graph of J. It's where you have a low height, boom, right there, height, a max height up here. Those are the minimum and maximum. Let's go ahead and label them. That is called the F min. This is called the F max. F max. Those 2 points need to be reflected in the graph of J prime. So I'm going to let you try that out on your own. But before I do that, when I take the derivative of a negative cubic, it turns into a what?
Quadratic. A negative quadratic.
A negative quadratic. And there it is. Give it your best shot. All right, so we're back, and the answer here is that this F minimum X coordinate here should be the same X coordinate here, same F max X coordinate here should be the same X coordinate here. They're equal distances from the origin, which is why it's not the best example. I think I'm going to change that for next year. I'll make a note to myself, but I'm going to do this in red. So I need to be going through here, and because I know it's a negative quadratic, I already know it's going to look like this. Roughly like that. Another reason that this works is this point right here. It is a relative extrema. It is what type of relative extrema again?
Which one? Oh, that's a minimum. F roll min.
F min. And how do you know this is an F min on the graph of J prime?
Because if you're going from the left,
If you're going this direction, negative to a positive. Exactly. And what about this point? Very similar. I know it is an F max because...
yeah, you look at it.
It's going from positive to negative.
Yeah, and we always assume you're going from left to right, so you can just say it goes from this to that.
Yeah, but it's
Without
confusing because of the arrows. But
Okay.
it makes sense.
Yeah, I understand that
Then
too.
how do you know where part of the y-axis you're supposed to go across to?
Yeah, should it be up there? Should it be more like this?
Oh,
That's a good question, and that's why we're doing a sketch. There's no wrong answer for the notes. There are wrong answers once you start giving, if I give you an equation, you need to be able to take the derivative and then graph that equation. Although I don't think I'm going to ever make it really that hard in terms of your graphs of the quadratic. You need to basically identify graphs. So if you can just look at a graph and say, hey, that's good, or hey, that's bad, that's all that I expect from you in this class. I don't expect you to know all of the general formulas to graph a quadratic. That's not tested on the AP test. Although if I was teaching a normal calculus class, I would probably expect you to do that. But we already have a lot of material to go through, so I'm not going to test that. All right, on this graph of J prime, there's an inflection point. Where is it?
What?
An inflection point. First of all, what is the definition of an inflection point?
Okay, what do you change?
Oh,
so it's in the middle.
A little bit better of a definition. It has to have the word F in it.
F prime. When F prime signs changes. Or no.
Close.
Double prime.
F
Yeah, F double prime sign change. So on the graph of J prime, what is J double prime? Is it the height, slope, or concavity?
Height, maybe.
concavity.
It's,
Wait.
yeah, all three of us gave three different answers. It's one of those. One of you got it right. I don't know who it is. Okay, so remember, heights, or whatever I give you right here, heights are represented by J prime. That means the derivative will be slope. So J double prime is slope. And we're looking for where J double prime does what for an inflection point?
No.
It changes.
0.
Yeah.
Changes sign. Exactly. So where does the slope change signs on this graph of J prime?
Like,
0.
yeah. Y
X
equals
equals
X equals.
Right there. And if I drew my graph correctly, it should have been right there because it should have been exactly halfway or the midpoint between these two x coordinates. It should have been right there, and we'll label that as the inflection point. This is some good review. All of this always needs to be at the tip of our tongues, and I like how good you guys are at getting that out fast. All right. Our final and fourth example. Ooh, what type of function is this?
It's like
First of all, is it positive or negative?
Positive.
And then go for it, Ben.
x to the 4th. How do you say the 4th degree?
In most classes, you'll say a positive polynomial, but I know that this is a positive quartic. And if you just say a positive polynomial, a positive even degree polynomial, you'd be correct. Or a positive polynomial with max degree of 4, that would also be correct. But I think quartic is the max you'll ever see on the AP test, so that's the max in our notes as well.
What about x to the power of 5th?
To the power of 5, I don't think you'll ever see it on an AP exam.
That would be an odd degree.
It would be an odd degree polynomial, which would mean you're doing what type of dance? Are you doing this dance, this dance, this dance? What type of dance are you doing for a something to the power of 5?
The ends go off in opposite directions.
Exactly, yeah. Rochelle has the dance down. All right, so for quartic, positive quartic, take the derivative, and it turns into a
Positive cubic.
positive cubic. All right. Whenever I have a graph, I want to always, and it's just the normal graph of k, there's no k primes. Whenever I see that, I always want to look for the minimum and maximums. Where are those guys? There's minimum right there, so we're going to label that F min. This up here looks like an F max, and we have an F min down here. Cool, cool. And that's really all we need to label from this graph. Look at those x coordinates. We have an x coordinate right there. And I should be doing this in blue. An x coordinate right here at 0, of course, and over here. Looks like this one is maybe a little bit closer.
For graph of k be the IP for graph of k prime?
Say that one more time.
So for the first f max, so the f max, would it be the IP for graph of k prime?
If this was a graph of k prime, then yes. Yeah. All right. Now I need you to do your best to sketch a positive cubic that matches this graph of k. So what's k prime going to look like? All right, so we're back. And it looks like everyone was able to correctly identify that the x coordinate here, x coordinate here, and x coordinate here should all have something special happening. We know that at an f min, we should be going from a negative height to a positive height, which means we have a graph that comes down like this. And in fact, the way that I've taught this in the past is just go like this, and then we'll fill in the graph later. I know that I'm going in that direction. I know at this point right here, I have a max, which means I'm going from a positive to a negative, so it should look like that. And then I know over here I have a minimum, which means I'm going from a negative slope to a positive slope, or a negative f prime to a positive f prime, so a negative height to a positive height, so it should look like that. And then you just kind of fill in the rest, so you know, okay, well that one should go like that one should go like that, and then this goes off and off forever, which matches with our definition of a positive cubic, because if I were to draw points at these ends, that line would be a positive slope. And everyone had roughly that graph? Yep. Cool. All right, where are our inflection points?
At 0?
Right there.
No, because the slope didn't change.
Ah, so the slope has to change on this one for inflection points.
Probably.
So they have to change. So where does that happen? It's very similar to our last example where it's kind of at the peaks and the troughs.
Yeah, that would
So
be
it would
it.
have 2 inflection points.
2 inflection points, they're in there. Yep, let's label those. Those are inflection points. That's an inflection point. And then I know I'm kicking a dead horse here, but I want to talk about this. This guy, what is he? Don't look at this graph. Just look at the right-hand graph. Just looking at this graph, is this a minimum or a maximum?
F rel min.
Yep, it's a F min, F relative min if you want to be very precise. Okay, what about this one?
Yes, negative.
This one is a,
Maximum.
why?
Because it's going from positive to negative.
Perfect. And then Rochelle, do this one.
F min,
Why?
going from negative to positive.
What is going from negative to positive?
The inflection point from, oh,
Is it the height, slope, or concavity that changes from a negative to a positive?
the height.
Yep, exactly. And then the heights are represented by k prime. So I guess all of these would technically be labeled k minimum, but I'm just going to leave it as f minimum because I'm lazy like that. All right. Just a bit of review. If you need this for your notes, even always points up, or they both point down. If you need this, you can write it down. That's a negative, that's a positive, and then odd. If it's positive, it looks like that. That's the positive, and then the negative version does the reverse of that, where it looks like this. That's the negative version. I know I already talked about that in the previous notes, but that's the difference between odd and even. All right, are there any questions on the notes today? All right, go ahead and write your summaries.